Excuse me. You're fine. Oh. Wow, we had perfect attendance 2 days in a row. Amazing. I have a little something for you today. If you could take one of these and just pass them around. There. Just kind of get these all the way around. If you could just pass those over there. And then I have another one for you. Okay, if you could take one of those and pass those around. You have a general question? What is your general question?
Well, whenever you're dividing, you always divide the bottom by the top when you do percents, because I found when in order to get the right answer, I always divide the top by the bottom number. It'll give me the right percentage. Is that wrong?
You have to give me an example of what you're talking about.
Like, one of the questions was 35 is 35% of 200. Not 35% of 200. I'm sorry. Is 35 equal 15% of what number?
Was this out of the homework?
It's out of the homework.
What number was it? Or what page? Well, we have different versions of this thing.
Here's an extra one of those. It shows red.
It is 35 is 15% of what value?
35 is
15% of what value?
15% of what value? All right, that's the question.
Yes, sir.
So you turn it into 35 equals 0.15 of means times what number is x? Like this.
And then divide it by 15, and then
So you divide 0.15 here, you divide 0.15 here. This turns into a 1x. And then on your calculator, 35 divided by 0.15.
and that gave me like 233.3 that way.
233.3? Uh-huh. Are you saying that you don't agree that that's right?
It
Or
just seemed too large for me. So
okay, so let's see. 35 is 15% of 35 divided by. It makes sense now?
it makes sense now.
Okay.
I think my math there just turned off.
Okay. So like, yeah, you just sit here and say something like, I don't know. What would 10% of this be? 23? Right? 15% should be a little more than that, 35. I mean, it seems to be reasonable. If you did it the other way, 0.15 divided by 35, you're at like 0.004 something. So 35 is 15% of a tiny number wouldn't make much sense. Any others?
Can that be done like this?
The same problem?
No, any problem.
What is this? Part whole, percent over.
See the formula that is over of equals percent over 100? That's how I did all of mine and got the same, got it right.
I'll say just very lightly, it appears like maybe you could do that. What I'm trying to do is get you to be able to turn a word problem into an equation. because solving an equation is something we want to be able to do, right? So if you have a way of doing it and you're comfortable with it, I'm not trying to relearn you or anything, you know what I'm saying? But if that falls apart at some point, you know, I can't say anything other than, well, that's not what I'm showing you to do. So, okay. All right, let's proceed. I did want to start class because there is some confusion. Understandably, there's confusion about the homework and the packets. There's two versions of the packet. The one at the bookstore seems to differ from the one online. And at this point, I don't think it's worth us, you know, trying to all get the same packet. So what I just want to be clear on is some of our problems might be a little different, but they're all going to be very similar. And when I cover a topic like today, if you could please flip to this section. We started percents last time, right? So if you notice in the section for percent, it says percent, then it says practice, or it says A, and then practice, and then it gives you problems, right? 10 problems there? On both packets, is that the same? And then below that it says proportion, and then it says part B, it says practice, right? That's what I'm going to do in class, right? Those are the problems I'm going to work through. The homework that corresponds to that should be on one of the following pages, and it will be titled homework, and then percent proportion, it'll have part A and part B. So you're supposed to do the homework for part A from last time because we covered part A. I didn't get to part B, so part B you will do for homework tonight. So that way we don't have to sit here and talk about page numbers because we have different page numbers. Is that clear enough for everyone? Okay, if you still don't have any idea, just talk to me after class and I'll show you exactly what I'm talking about. Okay, we're going to do proportion today, and then we're going to get into conversions. And I handed these out. Everyone have a copy? There's two of these. These are little conversion cheat sheets. I'm going to allow you to use these on your exam, all right? But this is the only copy I'm going to provide for you, so do not lose them. I will not have extras when it comes time to the exam. So we will get to those in a little bit, but we first need to start with proportion. Now proportions and percents, bless you, go hand in hand. And I think the best way to get into this topic is just to do a couple of examples, and then hopefully you'll kind of catch on to what's going on. All right? So let's take a look at this first one. I have here that one plain bagel, okay? So one bagel has 320 calories. How many calories are there in 2.5 bagels? So the question is, how many calories? Can't write today. Now, this problem would be, I think, really easy if it said how many calories are in 2 bagels, right? Because then you would just double that, wouldn't you? 2.5, you may say, well, I'll just multiply it by 2.5 instead of multiplying it by 2 for doubling. And yeah, you could probably get away doing that for a while until the problems become a little more complicated. So just like with linear equations, right? I gave you problems, it wasn't exactly this. Well, I think it was exactly this. I said, can you tell me what the answer is to this? And people looked at it and said, okay, if you put 2 in here, it'll work. And that only works so long. So we need more of a process. And so the idea behind proportions is a way that we can use fractions, which is what a proportion is, to solve a problem like this. So first thing, what is it that we want to find? How many calories, right? It's important that we recognize the unit that we're trying to determine. Trying to figure out the number of calories. And we're going to call that X, all right? So I'm going to say here, X calories, and I'm actually going to write the word down. And I'm going to set up the proportion. X calories in how many bagels am I looking? I'm saying how many calories are there in 2.5 bagels? So I'm going to put below this, I'm setting up a proportion or a ratio or a fraction. I'm going to put 2.5. And would you like to use the decimal 2.5, or do you want to stick with 2.5, or do you want to write it as 5 over 2? It doesn't matter. 2.5? 2.5 bagels. Okay. This is the proportion that I'm interested in. How many calories are there per 2.5 bagels? But this must be equivalent to or proportional to what's given to me in the problem, which is that one bagel has 320 calories, right? So what I'm going to do now is I'm going to set up another proportion next to this, or another fraction. It's going to also be calories over bagels. And this is my given information. How many calories are there? What am I told? I have 320 calories, right? Per one bagel, right? And believe it or not, we have a linear equation. And we have a lot of other stuff in here, right? But imagine the calories and the bagels and the calories and the bagels. Imagine that those weren't even there. Then what would that equation look like? X over 2.5 equals 320 over 1, which I could just write as 320. And do you see that that's a linear equation in X? And so to solve for X, how would I get X isolated by itself here? I'm dividing by 2.5, so how do you undo division? Multiply. So I would multiply both sides by 2.5, wouldn't I? Which is what I said we probably could have done to start the problem, right? But it's important to see that the way you'll do these problems is you're going to write down what you're trying to find, set up a proportion, and compare it to the given information's proportion or ratio. Understand? Now, I also want to point out that you could imagine, even though it doesn't seem right, when you have an equation you can multiply and divide both sides by something. Imagine, if you could, dividing both sides of this equation right here by the word calories. Right? So what happens if I divide this side by calories over here? It's like imagine coming in here and dividing like 1 over calories right here. And then doing the same thing over here. I'm out of room on my board. What if I did 1 over calories over here? What would happen? So what happens when you have calories divided by calories? They go away, right? And over here, calories over calories, they go away. And then what could I do to get rid of bagels on both sides? Multiply by bagels on both sides. So if I multiply this side by bagels, and I multiply this side by bagels, the bagels cancel out, and then you're here, right? Y'all kind of get what I'm saying here? So when you hear me say we want to cancel the units, because I'm going to say that throughout the day, this is what I'm talking about. We want the units, whatever they are, to go away. That's why it's important that when we set this up, we were looking for calories, so I put calories on top. And I put how many bagels there were. It would be incorrect for me to do this. 1 bagel and 320 calories. Do you see that if you do it this way, you can't get, this is not right. Do you see that you cannot get the units to cancel? Right? If I try and get rid of calories, I divide by calories here. If I divide by calories here, I create like a calories squared almost. And so the units aren't this, can't be canceled. All right? All right, let's try another one of these. I have a leaking pipe. A leaking pipe can lose 24.7 gallons of water in a week. So pipe loses 24.7 gallons per week. It says, how many gallons are lost in 30 days? How many gallons lost in 30 days? All right, let's try and do this systematically. What is it that we're looking for? How many gallons, right? How many gallons? So I'm going to call that X. X gallons is what I'm interested in. And I'm going to set up this ratio over what am I looking at now? How many gallons? What? Lost in 30 days. So I'm going to put down below it 30 days. Now I need to set this up as being proportional to the information I'm given. Do you see the danger here? Do you see what's about to happen? You have gallons, right? So I want to put gallons here, and I want to put over here what? Days, so that they match up on both sides. But the issue is that I'm told that the pipe loses 24.7 gallons per week. And so I cannot put days here unless, well, I convert, right? I have to convert. How many days are there in 1 week? 7. So this is an easy conversion because we all know that there's 7 days in 1 week, right? Yes? But let's see how you do it technically, all right? So the problem right now is that I'm given weeks here, right? And I want it in days. Yes? Okay, so I'm going to write down this right here. 24.7 gallons. This is scratch work on the side per 1 week. This was given, right? But instead of gallons per week, we want gallons per day. So you said, well, this is just 7 days, big deal. The proper way to do that is to multiply this by what's called its conversion factor. So we want to convert weeks to days, right? Weeks to days. So I want this bottom to be days underneath instead, right? So I'm going to put days down here. Now just follow me if you can for a second. And up here I'm going to put weeks. Now notice what happens if I multiply these two fractions together. The weeks will cancel, won't they? And you'll be left with gallons over days, right? Which is what we want. But I need to now know what this relationship is. What is the relationship between weeks and days? Well, 1 week, right, is 7 days. And so I can cancel these out and then multiply straight across. So 24.7 times 1 would give me 24.7 gallons. And then over, what, 7 days. Like I said, you could have done all that without even writing all of that down. But when we start converting like ounces to liters or inches to kilometers, we need these conversion factors to be able to do that. All right, so let's plug this in here. 24.7 gallons over 7 days. All right, so let me see. Where did we live? We went all the way around the room last time? We did, right? Okay. Let me see. Don't feel insulted if I don't remember your name, okay? I know Caesar for sure. Yes? And then I want to say Ember. Ember? Is she not here? She's not there. Ember, where are you? And then Brittany, huh? Bethany? Don't tell me. 2 letters. JD? DJ. DJ. Okay. Okay. All right. Look, let's get back to the problems. I'll work on your names. But I do want to volunteer from this table. Can't be Caesar. So who's going to volunteer to tell me what you want to do with that? Any ideas?
Actually, I had a question.
Okay, go ahead. What's your name?
Can we, Shivani,
Shivani. All right.
can we do the cross multiply?
Yes, you can.
That's how I learned.
Okay, very good. So remember way back, who said cross multiply like first day? I think you were sitting over there and you said cross. Okay, so this is the proper way. Whoever said it, this is the right time you can do cross multiplication if you have an equation. Now, I'm not going to do it that way, but we're going to be doing the same exact thing. All right, we're going to be doing the same exact thing. How about the units? How about gallons, gallons, days, days? Can I just like ignore those? Yes? I can, right? Because you could basically divide out gallons on both sides. You could multiply both sides by days. And now you have a linear equation, don't you? I'm going to stick with you. If I write this linear equation down, I'd have x over 30 equals 24.7 over 7, yes? All right, so let me now get back to your proposition, which was just to cross multiply. How many of you have seen that? Cross multiply, and you love that stuff, don't you? Cross multiply. Here's the reason I don't like to encourage cross multiplication at this point. What are you trying to do? What's your goal here? Solve for x, right? What's the only thing you need to do to solve for x right now? Multiply both sides by 30. There's no need to multiply the left side by 7, which is what you would do when you cross multiplied, right? You go like this. Why multiply by 7 and create a 7 in front of the x when you don't need a 7 in front of the x, right? So this goes back to the fundamental idea here is we have a linear equation we're trying to solve for x. That's it. Do what you have to do that. I'm going to multiply both sides by 30. If I multiply 30 here, multiply 30 here, and I will be done, won't I? If I do that? I'm going to have to do all this, right? Okay, I'm going to do that, but let's just see. On the left side, the 30s would cancel. You get x equals, and now I still need to figure this out, and I will break my calculator out to do this. What do I do first? Multiplication, division, doesn't matter. Work left to right. On your calculator, 24.7 divided by 7. And take that answer and do what with it? Multiply by 30. And you get x is 105.86. We'll just round 2 decimal places. There you go. Now, Shivani, you would have got the same thing. You would have had 7x equals, and you would have done the 24.7 times 30, right? Yep. And you would have had 741, correct? And then you would have divided by 7. So at the end of the day, we all wind up with the same result. I'll leave it to you. You want to cross multiply? Go ahead. But I'm going to stick with we want to solve a linear equation as the underlying goal. All right? Questions? 105.86 what? Gallons. Let's not forget, how do we know it was gallons? Well, look at our x, right? It was x gallons, right? So now let's read back through the word problem. Pipe loses 24.7 gallons per week. How many gallons does it lose in 30 days? Well, 30 days is longer than a week, right? It's actually like more than 4 weeks. So our answer should be more than 4 times this, which it is, right? 105.86 makes sense as an answer. And you always want to do that kind of mental check. Like if you got 2 gallons, you'd be like, wait a minute, hold on. I'm supposed to lose 24.7 in a week and I got 2 gallons in like 30 days? It doesn't make sense. Questions? Y'all like these? Like is a strong word. You love them, I understand. How about number 4? Does everybody have a pre-election survey? Number 4, pre-election survey. 5 out of 13? Everyone have 5 out of 13? How many people do you have? 5850? 5850? Okay, let's work that problem. I don't want to write it all down. We're going to move to the next table. Whoever, it can't be, well, it can't be, what was her name? Ember. It can't be Ember because she's not here. So read through the problem. The pre-election survey showed that 5 out of 13 registered voters would vote in an election. At this rate, how many people would be expected to vote in a town of 5850? So I'll ask for a volunteer, but I'll guide you if need be.
Well, I think you set them up next to each other.
What's your name?
Carlos.
Carlos. All right, Carlos. Set them up next to it. How do you mean?
Like 5 over 13
Okay.
equal to x over 5,850.
Okay.
Equivalent to it.
I think that sounds pretty good. Let's write down what we want first, right? So what do you want?
You want x.
X, which is going to represent,
How many people would be expected to vote?
okay, this is the number of people expected, I'm just going to put expected to vote. Is that all right with you? Yes, is that okay? And we want to know that in relationship to what?
To 5,850.
Okay, the 5,850, I'll put voters. So how many of the people, right, are expected to vote out of the 5,850 voters possible? Okay, keep going, Carlos. What do you want me to do now?
I think now you set it up the 5 over 13.
Okay. So
That's the proportion of people expected to vote.
expected to vote. They expect 5 to vote out of every 13 voters. That's not a 13. What am I missing, Carlos?
Answer?
Yes, but you can't really.
The equal sign?
The equal sign, thank you. Okay, so I need the equality there so I can solve an equation. And now, am I allowed to start canceling the units out?
Yeah.
Yes? And the linear equation now becomes x over 5850 equals 5 over 13. Now, let's just do a vote. And I'm not going to hold this against you. How many of you are just you're going to cross multiply that no matter what I tell you? It's okay. That's fine. What is it?
If you don't want to cross multiply, you do what you did for the last problem.
Yes, what would that be?
5 times 5,850.
You would do your 5850 right here and your 5850 over here. And if you're multiplying, it's really a 1. I didn't write that last time. It's really a 1, right? Over 1. But that's the multiplication. That will isolate your x, and you're there. You just need your calculator now. Do you have one, Carlos? I'm going to let you take this one all the way if you want.
No, I've been slacking on getting myself.
Okay.
I'm going to use my phone.
Okay, I'll let you use your phone for right now.
Oh, actually.
It'll be, okay.
That's nice. Thank you. Well, 5,850 times 5 comes out to 29,250.
Okay.
And then you divide that by 13, the number on the bottom,
Mhm.
comes out to 2,200.
50?
Yeah.
There it is. What does this number represent?
The senior citizens and middle-aged people.
The number of people that are actually expected to vote out of this population, right? All right. So I'm trying to give you a systematic approach to this. All right. Hopefully it's starting to make sense. Is everyone on board? Anyone have any questions? Pardon?
I have a question for that last part.
Uh-oh.
Let's just say that we have to figure out what that percentage was compared to the number of people.
Okay, so what percent would that have been?
Yes.
You would do this number divided by 5850.
Okay.
And it's actually going to be the same as what you would get if you did 5 divided by 13.
Yeah.
Because the percentage, that's what you're using. When you say something's proportional, you're saying that the ratio of the two fractions is equivalent, which means when you divide the two fractions, both of those, you get the same result, same decimal.
Okay.
All right, let's look at, oh, I like number 5. Where's my brave table to do number 5? Where's my brave table? Do we have a brave table in here yet? You're the brave table?
Sure.
All right. Okay. You're taking everyone with you. All right, so to estimate, we're doing number 5. To estimate the number of trout in Big Bear Lake, a sample of 48 trout were captured and tagged. After releasing them, a net captured 300 trout, of which 9 were tagged. What would be a good estimate for the number of trout in Big Bear Lake?
All right, so the x over 48.
Okay, so what would be, so what is x? Can you tell me what x is?
The number of trout in the lake.
Okay, so can I just put trout in lake? Is that okay with everyone? Now what? That's what we want, right? The number of trout in the lake?
Yeah.
Okay.
Okay.
By the way, this is the hardest problem, all right? It's different. It's a little different than the ones we've done.
Just inverted.
How do you mean?
This one, the number of trout that I tagged is over the amount of trout in the lake. So, the ones captured, 9 were captured, and there's 300 trout in the net.
Okay, so yeah, let's try and understand that sentence. After releasing them, a net captured 300 trout, right? 9 of them were tagged. So what we have in this problem are two units. We have the number of trout, and we have the number that were tagged, right? Those are our 2 units that we get to play with. So you need to set up a proportion here, and you need to make it equal to something over here, right? That's the whole goal, right? Over here, this is going to be trout, right? And this over here, the bottom one, the bottom unit is going to be what? That's the thing I think that's missing here. The tagged trout, right? I'm just going to put tagged. Tagged. Sorry about my G's. They look like E's. And my E's look like G's. So do you know anything about this proportion over here? Yeah, there was a moment when they captured 300 trout and 9 of them were tagged, right? So we can put that over here. 300 over 9. But what about this? Yeah, so think about this. This was just when they caught the 300, right? And 300, 9 of them were tagged. That was the proportion or the ratio here. What we're looking for is the number of trout in the lake, the entire lake, right? Yes? And we know that they tagged 48. There's only 48 trout that have been tagged. That's it, right? Just 48. So this should be 48. Any questions? The big difference, I guess, in the two fractions is that this was when they went out and caught 300 trout, right? So this ratio has to deal with that one capture of 300 trout. This ratio has to do with the entire lake itself. All the trout in the lake over all the trout that have been tagged in the lake. And once you get that set up, it's just the equation now, right? So I can cancel trout, tagged, and do your work. Anyone have it yet? 1,600? Trout. So there should be about 1,600 in the lake. Yes?
Would you be able to reverse that?
How?
Like 48 over the X amount and 9 over 300. And so do the same answer?
Yes, but let's take a look at that real quick. All right? Every problem I've done, I've always told you, like, put what you are looking for over, right, and do that. If you would have written down instead 48 tagged over X trout, that would equal, then you would have to flip this one over, 9 tagged, right, over 300 trout. And then you would cancel the units out. And what you'd be left with is 48 over X equals 9 over 300. You still with me? And the only reason I don't do it that way, which you'll get the same answer, all right, is that this is not a linear equation in X. This is called a rational equation in X because X appears in the denominator, and that creates what we call a rational equation. Rational equations, there's a different method to solving them, and so I'm avoiding those by always putting X on top. Now here, you would actually, to get X by itself, you would have to multiply both sides by X. This X would cancel, right? And then you would have to multiply this side over here by 300 and divide by 9. Multiply this side by 300 and divide by 9. And guess what? We're going to do the exact same computation that we just did. Does that answer your question?
Yes. So you could take the rational equation, assuming that units are the same or non-existent, and flip them to put X back on the top and solve that way again.
Flip the ratios, just flip them over?
Yeah.
Sure.
To turn it from rational
Yep.
to a linear equation.
Sure. All right, let's move on. Applications of percents. So this is something that we deal with regularly, and that's money, right? So a couple of formulas. If you go to buy something and you're going to pay sales tax on it, or tax, it's going to be the price that's listed on the sticker plus the price times the tax. And the important thing is that when you write that tax, this tax must be converted from a percent to a decimal. That's the first major thing we need to remember. And then the next formula is how you figure out what we call percent increase or decrease. Like when something goes on sale, the price has been cut, we can figure out what the percent decrease is. Or if your utility bill went up this year, you could find the percent that it increased. And the way to do that, the formula that we use here, they write the word, yeah, they use the words new minus old over old is going to be equal to the percent increase or decrease, depending on whether or not the answer is positive or negative.
You have to multiply it by 100 as well.
Yes, this is the percent, right, as a decimal. So you're going to have, how do you want to do this? Let me see. Let me slide this in here. Hold on. Yeah, no, I'll just leave it like that. I'll put the 100 on this side. Like that. Yeah, because it's going to give you a decimal, and then we can always convert a decimal to a percent. All right, so that's it. Let's look at one of these problems. And when I said, when they say new and old, they mean the price. The new price minus the old price over the old price. You could say new minus original over original if you wanted to. New price minus original price over original price. Multiply that by 100. So Amy bought a pool hall, you know, because it's pretty common to go out and buy pool halls. I think I might buy one this weekend for $219,765, right? This price includes a 5% sales tax, state tax. What was the price of the pool hall before tax? All right. So we have that Amy bought this for $219,765. Now you tell me, is that the price of the pool hall, or is that the price before tax, or is that the price after tax? After tax. So that's the total that she paid, right? If you go back to the formulas we had total was equal to price plus price times tax, right? I'm going to use P instead of price and T for total, right? That's the formula we had. So we actually know that that number is T, isn't it? The total? Yeah. And we want to know the price before tax, which was P, yes? Do we know anything else? The tax is 5%. So what I'd like to do is rewrite this equation right here, replacing everything that I know goes in here with the values. So T is 219,765. Do I know what P is? No, that's what I want to know though, right? P plus P, and then do I know the tax rate? 5%, I can write that as 0.05. That all right with you? That's multiplication here. What type of equation is this? Linear, right? If you replace those p's with x's, this is a linear equation. And so all you're trying to do is solve for p, right? Get p by itself. So you go to try and get the p by itself. You have two p's over here. How can you work with this over here? What can you do? What's that? Combine them together, right? So I think I'll write it a different way. This is really like 1p plus 0.05p, right? That's the same thing. Writing the number in front of the variable instead of after. And then this side is 219,765. And then combine these together. So you just add them up, right? So what's 1p plus 0.05p? 1.05p. And final step, divide both sides by 1.05. So I'll do that on my calculator. 219,765, divide that by 1.05, and I'm getting $209,300 is P. So when she went to purchase the pool hall, it was on sale for $209,300. She paid 5% tax and turned out total this. Yes?
So what if you do like the total times 0.05 and then you get how much the tax was and then you minus that from the original price?
If you do what now?
So like $290,765
Mm-hmm.
times the tax, which is 0.05, and then you get however much like the tax was out of that, minus it from the original price.
That should not work. And the reason why is because you're taking 5% of something that already has 5% on it,
Okay.
right? So that number came from someone taking 5% of some number. So, I mean, let me just show you. 219,765 times 0.05 would be $10,988.25. That's how much it would be. That's 5% of this. If you take that away from that, you will not get this number.
Right.
It'll be off. So you can't do it that way. There's kind of a trick to it. If you want to, this is like if you've gone to buy something and you're trying to find your subtotal before tax, and all you're looking at is your total. All you have to do is take this number and divide it by 1 point, then whatever the tax rate is. So like if the tax rate here was 5%, notice we divided by 1.05. If the tax rate was 7%, we would do 1.07. If the tax rate was 10%, you would do 1.1. Because every time you do this, you're going to do 1 plus, right, whatever this is. That's always what's going to happen here. And then you're going to divide that through. All right, can we move on? Yep. All right, Steve needs to buy his sister a birthday gift from the mall. He sees a shirt that is normally priced $24.50, but it's on sale for 20% off. If the sales tax is 8.25%, how much will Steve pay for the shirt? All right, so we have a shirt, $24.50, but it's going to be on sale for 20% off. The tax rate, written as a decimal, is 0.0825. That's all the given information, right? How much is he going to pay total for this? So how do you want to approach this?
24.50 times 0.20.
Yeah, we're gonna wind up using this formula right here. Right? We're going to wind up using that formula. But we need to know the price of the shirt. And the price of the shirt originally is $24.50. We need to figure out how much it's going to be after 20% off. Right? So this right here is not P yet. We have to take the 20% off. So how do you take 20% off of something? Okay, so what do y'all think about that? If I multiply 24.50 times 0.20, what will that give me? That's how much I should take off, right? Do y'all agree with that? And what is that? For what? 490? Yeah, 490? Okay. That's how much the discount is. And then what we need to do is take that number and subtract it from this number.
19.6.
19.6. So if I take the original price, $24.50, minus $4.90, you get what? 1960. So that's going to be our P. How many of you are okay with that? Yes? Does anybody have a more efficient way? There is a much more efficient way. What is it?
Multiply it by 0.8.
There you go. So look, if there's two ways of looking at this. If someone's going to sell you something and give you 20% off, you can go about trying to figure out how much to take off, or you can just try and figure out how much that is. So if someone takes 20% off of something, you're really only having to pay for 80% of it, right? So you can do all this work, and if everyone's happy with that, fine. But the more efficient way to do it is to say this. Take 24.50 and multiply it by 0.80. That's 80%, right? So instead of figuring out 20% off, I want to know what 80% of the shirt is. And if you multiply that, what do you get? 1960. That's much cleaner to do it that way. But they both work. That's how I do it. Like whenever something's on sale, I always multiply by this number. I don't go try and figure out how much to take off. I always just multiply by that. Okay, so that's our P, right? That's P. P is 1960. So the total we're going to pay is going to be 1960 plus 1960 times 0.0825. So I'm putting price, tax. And let's see if you all followed me a second ago. What did I say when you put these two together? What are you always going to get here? 1 point. Oh, sorry. Just act like I didn't say that. We're not solving for P. I apologize. Just multiply this out. I call those brain farts. Get your calculator out. Times 0.0825. So I'm doing the multiplication first, right? Do that first before you do addition. So I'm going to have 1960 plus 1.6. I'm going to say 17 because that's what my calculator told me. And then I'm going to add those up. 21.217 is what I'm getting on my calculator, right? Is that what you got? But this is money, right? So we can't have that. So what do you think the store is going to charge them? $21.22, right? So the price total out the door is going to be $21.22 if we round up. Yeah. So the tax rate in San Antonio is about what, 8% or so, a little more than 8%. So whenever you see these discounts, right, of 10% off, that's basically just killing off the tax, right? That's basically what's happening, roughly. A little more, but. Here's a question. What do you think is better? Let me try and see how I can phrase this question. Do you think it's better to get 20% off of, like a sale on an item? Do you think it's better to get 20% off or to get 10% off twice? Or is it the same? This actually happened to me when I was buying something at Lowe's. I had a coupon for 20% off, but then I had another one for 10% off and then a military discount for my niece, And so we were going to get 10 followed by 10, or we get 20%. And the person behind the desk was telling me it's the same thing. So they were like, it doesn't matter. And I was like, it does. So it does it. Let's see. Let's just say that I have 20% off of a price. Okay, 20% off. Then that's just going to be, how much would I get off? 0.2, right? 0 times P, whatever the price is. Let's compare that versus 10% off first, right? So if I take 0.10, 10% off of a price, and then 10% off of that, which means I take this thing and multiply it by 0.10 again. Right, so whatever this price is, right, take the 10% off. Let me do it a different way. Let's use a number. Can we use a number? I would think it'll be easier if we use a number. Let's use $100. Okay, $100. How much would that be? 20% off of 100. How much is off here? $20, right? It's $20 off. With me? Okay, let's do 10% off of $100. So how much would that be off? $10 off. So right now, how much am I going to pay for this one? 80 bucks. And over here, I'm going to pay how much? 90. But I get to take 10% off again. Right? So take 10% off again. What's 10% of 90? $9. So when you take $9 off of 90, you get $81. So I'm actually going to pay more if I do 10% twice than I would if I do 20% once. Now that may not make a big difference if it's a $100 purchase or a $10 purchase, but if it's like $6,000, you're going to save yourself some money, right? Okay. I don't know what made me think of that, sorry. All right, let's do one last problem out of this section. And then we're going to take a break. And what I'd like to do on our break today is I'd like to walk around. I'd like for you to just kind of take out your homework. And I'm going to just come by and I'm going to take attendance today off of that you have some homework done. And I'm going to count that as a quiz grade. All right? All right, so we are going to do Kelly takes her friend out to lunch and pays for the bill. Her friends insist on paying the tip. If the bill was $38.75 and they want to leave a 15% tip, how much money will they need to leave? The bill and the tip included. You don't even need this anymore, right? The receipts, most receipts at restaurants will print out on the bottom what, the tip, the common tip percentages. I'm not ashamed to say that when I was a student, I waited tables. In my opinion, waiting tables as a student is an absolutely great way to get through school. You can make your schedules, you can have people work for you. If you're broke and needing money, you can pick up a shift. Okay, you have to deal with people and food, that sucks, but one of the things that people in the wait tables know is, is this 15% that you're supposed to get tipped off of the total or off of the subtotal, before tax or after tax? What do y'all do? Do y'all just tip off of, do y'all tip?
After tax.
Y'all do tip, right? Okay. You just tip off the total? Yeah, it depends, right? I mean, some people will say it should be subtotal. Some people say it's total.
The cheap people say it's subtotal.
Yeah, exactly. Okay, so what are we going to say here? Because they're asking us to figure out what the tip should be. That's the total bill. Are we going to go off the total or off the subtotal?
Total.
The total. We don't know anything about tax, do we? So there's no way we could go back to subtotal here. So we're going to assume that we're going to tip on that total. So how much will the tip be?
The tip is $5.81.
Okay, so you're getting that by taking 15%, 0.15, right? And you're multiplying it by 38.75. And what does that come out to be?
$5.81.
581. And that's how much you need to add on top of the amount, right?
44.
So 38.75, you're going to add to it 581. And what is it? 44.56. Now, I'll just say for the record, I think that 15% is too low. I think 20% is your minimum these days, just because of inflation, all right? Not because the service is better nowadays.
For a long time. Set up right there.
Yeah, so that's it. We've all done tips before. How issue is going to be whether or not you can take a test, right? That's where a lot of students get hung up. You know, they can do the homework, they get to a certain level of comfort, they come to the test and it's like, you know, I blanked, I couldn't remember anything, I freaked out, I panicked, right? I mean, I'm sure you've never heard that or felt that before. This way. So here's some advice on preparing. You don't need to sign in, I checked you off. This is just going to go for the people I couldn't check their folders off, so those 3 tables. One of the best things you can do to get ready for an exam is to pick some problems, you know, from each homework assignment or problems that I've done in class, and sit down in a testing environment, turn off the TV, turn your phone off, and start doing the problems. And just your calculator and you. And if you have trouble doing that at home where you're comfortable, you're going to have, you know, twice the difficulty in a class like this. So you want to at least start to acclimate yourself to that sort of environment. And so when you're sitting there, if you're frozen on a problem, then you need to kind of write something down, say, all right, you know, look through your notes. What did you need to do that problem? You know, just make a little note to yourself. So try to identify where your weaknesses are, is what I'm getting at. But if you don't practice the testing environment, don't be shocked when you come in here and freak out, right? It's like, you know what, I watched people run marathons, I've seen it happen, you know, and then I never practice and I go try and run a marathon, it's not going to happen. All right. So we will proceed, and now we are going to get into conversions. And scientific notation is what we're going to start with. So Jose's not here, and Zachariah, is that correct? And Ember. We almost had perfect attendance for 3 days. All right, so scientific notation is a short way of writing big numbers or small numbers. So if I have a number like, you know, 2207000543796. Now that's a pretty big number, right? Yeah? In fact, if I put in my little commas in here like that, then we might even have a name for that number. Let's see. These are tenths, hundredths, thousandths. Ones, tens, hundreds, thousands, 10,000, 100,000, million, 10 million, 100 million, billion, 10 billion, 100 billion, trillion. And I believe if we put a 1 out here, we would get to like 12 trillion. I think our country's debt is past that. Okay, it's good to know. So these are big numbers, and a lot of times when we're writing numbers like this, if a number is that big, this stuff really doesn't matter, okay? This stuff is insignificant compared to the size of the number. So we can use what's called scientific notation to have a shorter way of writing this. And so what we need to do is identify the decimal place, which would be a decimal back here, and then there's zeros back here. And we count how many decimal places does it, or how many places until we get to right before the first number out there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? 13 spaces. So what I'm going to write is 1.22. I think that'll be good. I'll just go the first 2 numbers right here after the 1. 1.22, and then I'm going to write times 10 raised to the 13th power. That's the scientific notation. And I think a lot of people don't see that, like, they don't realize really 10 to the 13th is just a number, isn't it? It's a 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros. So what happens, you tell me what happens if I take a number and I multiply this number by 1, what would it be? Itself, right? What if I multiply it by 10? What would happen? It would become 12.2. What if I multiply it by 100? It would become 122. What about by 1,000? Just keeps moving the decimal. This is saying move the decimal over 13 places to the right. So I'd wind up back at this number. Do you all see that? Well, I wouldn't have the 7 and the 5 and all that. But like I said, the number's so big it's not relevant in this problem. Got it? So this is just a short way of writing a big number. Then times that number just has the effect of moving the decimal over. Now, we do the same thing if we have a small number. We have a small number like 0.0000000124. Then what we want to do to put this in scientific notation is take the decimal here and move it to the right until we get right past the first number. So I would have to move 1, 2, 3, 4, 5, 6, 7 spaces, right? 7 spaces. And I would write that this is equal to 1.24 times 10, but instead of writing 10 to the 7th, I write what? -7. And a lot of people think of this as, okay, if it's positive, you're going to move the decimal place to the right. If it's negative, you would move this decimal place which way? To the left to get it back. But please understand, 10 to the -7 is really 1 over 10 to the 7th. So there's a property back when you're learning about exponents that says if you have a number raised to a negative power, that's 1 over the number raised to the positive power. I don't know, does that look familiar to you? Negative powers mean drop it down. So when I write 10 to the -7, I really mean 1 over 10 to the 7th. And so what this really represents is the number 1.24 being divided by a huge number, 10 to the 7th, which makes it very small, which is why it's this. So all you need to know, I'm not trying to confuse you, all you need to know is what this represents. 10 to the 13th means a really big number, 10 to the -7 really small. And it makes arithmetic a lot easier, especially if we can use our calculators. So everyone's required to have this calculator. I said if you don't have this one, you're going to have to kind of wing it with whatever you have, right? But this calculator actually has a key, and the key on it looks like this. Times 10n. See if you can find that key on that calculator. If you don't have that key and you have a different calculator, I'm going to have to show you on your calculator what to do. So what I'd like for you to do, everyone who has this, did you find it? Okay. We're going to do no? Okay. How many of you don't have this calculator? All right, so we're going to have to wing it. We're going to have to figure out how to help you. What I'd like to do...
It's okay if it's a different variable. Mine says x.
Let me see. X to the n won't work. Oh, 10? Yeah, that's right. Yep, that'll work.
10 to the x.
But yeah, if you have time, 10x, something like that, that'll work also.
What if it just says 10x?
Let me see. No, yeah, that'll work too. See, that's what I'm saying. I'm going to have to go around and show each of you. Let me put the problem up first. Let's make sure that you're going to try and get this on your calculator, all right? I'd like for you to do 9.87 times 10 to the -3 minus 1.25 times 10 to the -6. I'd like for you to try and do that on your calculator. And I'm going to put what the answer should be, and let's see if you can get to this. Okay. So try it on your calculator. How many of you got this? Okay, that's a good sign. How many of you have a calculator right now but are not able to get this? One, just one, two, three. Okay. So there are only 3 people can't get it? You can try and help them out? Your key, you're going to use this little EE key. I know it looks weird, but do 9.87. No, go 9.87. And then hit the, yep, that's it. And then hit -3, so -3. Now minus, and then 1.25, E again, -6. There you go. Got it? That's what that key is. Did you got it? Okay, okay. All right, who else? Anyone else?
I can't find my caret key for the exponent.
Did you use that one?
Yeah.
Just try typing in a number right now. Wait, no. Here, let me see it for a second. Let me just see if I can figure it out real quick.
I brought the manual, so I'll go through it later.
Okay, so look at the way this works. You just type the number right behind it.
Okay.
So go ahead and just put in 9.87. Then hit that little time saying, and then put, no, -3. Back that up. Yeah, -3, and then minus 1.25. And then -6. Bam. Okay, so yours gave it back to you in scientific notation. Let me talk about that. Okay, so look. This is the answer that a lot of people are getting, yeah? Okay, I would like this in scientific notation now. So that means you're going to take this and move the decimal point over until you get right past the first number. So how many spots is that? 3. And since we're moving it to the right 3 spaces, we're going to be using 10 to the -3. So it's going to look like this. 9.86875 times 10 to the -3. I will say for these problems and for most problems, 2 to 3 decimal places is okay. Yeah. 3, I'm happy. 2, okay, that's fine. But you might run into some problems later when we're doing problems, finding solutions thing. If you round too much, your answer is going to be way too far off. For now, let's say 3. All right, if you have the TI 30XS, you can actually have your calculator always give you the answer in scientific notation by going and clicking on, or selecting the mode key, which is next to the green top left, and then going down on the second line it says norm, psi, and eng. You see that? And if you select psi and hit enter, and then quit and go back to your main screen and type that in again. Type this problem in again. Oops, sorry. Let me turn my phone silent. Type this problem in again. It'll give you this result. So just so you know, you can switch it from scientific notation and back out. All right. Now there are now what we call the metrics prefixes. I think that's a typo, but I could be wrong. I've never heard these called the metrics prefixes. Metric prefixes? So the metric system is the system used by most of the world except for us, right? The metric system. It's a way of measuring things, and they use what's called the base 10 system. And that's wonderful because the numbers we all use are base 10. And where's that little, you have that little sheet of paper? I gave you a list. You keep that one. You get one of each. Okay, so I'm looking at the one that looks like a table. So if we have a unit that we're trying to measure, and we want to look at this unit and let it get larger or smaller, we can use these abbreviations to represent how big they are. So how about let's do something that we've all heard of before. Bytes. So what is a byte? Terabyte, you've heard that. Gigabyte. This is computer lingo, right? So a byte is something in a computer that we won't get too technical here about. But it's the unit that somehow measures how much data can be stored. It's really just zeros and ones, that's all it is. But a byte is an amount of information. And if we have 1 byte, we could have 2 bytes, 3 bytes, all right? If we have 10 bytes, right? If we have 10 bytes, and let's just use B for byte, okay? If we have 10 bytes, we can say that that's equivalent to 1. So go on this table, go from, notice in the middle it says, the line that says 1,000 to the 0, and then it says none. You see that there? You'll see that? It's grayed out in the middle. Go 1 step up, and do you see that if you have 10 to the 1 above it, this was supposed to be 10 to the 0. If you see 10 to the 1, what do we call that? What's the prefix symbol for that? Deca. So 1 decabyte would be 10 bytes. So you take 1 byte, take another one, take 10 of them, and now you have 1 decabyte. What happens if I have 100 bytes? What would 100 bytes be? A hecto, right? A hectobyte. What if I take 1,000 bytes? Or sorry, yes, 1,000 bytes. A kilobyte, a kilobyte. Now we don't see kilobyte very much, do we, on computers? I mean, we sometimes do. Megabytes we do see, right? So 1,000 bytes is a kilobyte. Now we start using KB. That's what you'll see like on a computer, KB. When you attach, like if you look into, you've got some Word document and it might say 1.5 KB, so that's kilobytes. 1,000 bytes is a megabyte, right? What's after a megabyte? Gigabyte. Now we're starting to use words that we see a lot, right? Your data usage on your phone. If you have a plan with a cell phone carrier, you may have like, you know, whatever, 15 gigabytes allowed for the month, right? That's how much data. So a gigabyte is how many bytes? A gigabyte is how many? How many? A billion? So you look at that number on the side here, on the far right. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. There we go. Thousands, millions, that's 1 billion bytes. So if you have a billion bytes, that's 1 gigabyte. So when you're sending your little video to your friends through your Snapchat or whatever it is, it's sending it through, right? It's data. That data is measured in bytes, and you're sending so much of it that you're using a billion bytes of data. Go with me? And what comes after gigabytes? Terabytes. Now we're not there yet when it comes to like our data plans, right? Nobody here has a terabyte of data on their plan? No, because that would be what? How much is a terabyte? A trillion bytes. That's a lot. Now, some of these external hard drives or internal hard drives for computers are terabytes now. The gaming systems, yeah. And then you have, now we get into the bigger ones, right? Petabyte. We're definitely not to petabytes yet on standard computers, home computers, right? We're not there yet. But one day we will be. It's a quadrillion bytes. And then exa, zeta, yotta. Those are numbers that are so large, it's hard to even understand how big those things are, right? All right, we all okay with this? All right, now this whole scale, this metric scale gets bigger and bigger and bigger, but you can also get smaller. Now we can't break bytes down, so let's use something a little easier to work with, which would be a meter. So if we have a meter, that's our standard unit, 1 meter. 10 meters, this is like a meter right here, close. All right? This is how long a meter is. If we have 10 of these, it would be called a what? 10 meters would be a decameter, right? 100 meters would be a hectometer. 1,000 of these lined up together would be a kilometer. But let's get smaller. What if we take one of these and we cut it into 10 pieces? So take one, cut it into 10 equal pieces. So let me see. 10 equal pieces, let's say. Then each of these would be, according to this, 1/10 a decimeter. And if we cut each of these into 10 more pieces, each of those would be a centimeter. And if we took each of those centimeters and cut those into 10 pieces, we would be, what, millimeter, then micrometer, nanometer, picometer, I can't even say it, picometer, femtometer, attometer, zeptometer, yocto? Sure. The great thing about the metric scale is that everything is a multiple of 10. Everything grows in factors of 10. And so it's very easy to work with the metric system. So let's do a problem here. Let's convert here. See if you can do this. 4.7 kg into Gs. So this letter here is the unit, the base unit. In this case, we have to know what the G stands for. Does anyone know what the G stands for? Grams. G is grams. So we have 4.7 kg. Kilograms is how many grams?
1,700.
What is it? 4,700? How are you doing that?
Move the decimal.
Move the decimal. How many places? So you're taking 4.7 and you're moving the decimal to the right. How many places?
2.
2?
Sorry, 3. This is the
3?
place.
So how are you doing? How do you know that? You just know that?
Oh,
Kilo is 1,000. So what you can do is you can go to your table, right? And you find kilo. So find kilo on your table. It says K. Over here on the far right says 1,000, right? Where is just grams on this chart? Well, it's not, right? It's the base unit. So it's the column that says none, which is the column that says 1. Do you all see that? Yes? So kilograms is here at 1,000. The grams is here at 1 because that's our base unit. So how many steps does it take to get from the K, the kilo, down to grams? So you just count them. It takes 1, 2, 3 to get down to the gray one. Follow? And since you move down, if you move down on the chart, you're going to move your decimal point to the right. So you go 3 places to the right, and the answer is 4,700 grams. So if you go down on the chart, decimal place moves to the right. If you go up on the chart, decimal place is going to move to the left. Let's do another one. How about 0.98. I'm going to make this one up. Centigrams is equal to how many picograms? Pico. So find centigrams. Do you see centigrams on the chart? Well, you see centa, right? Centi. What does it take to go from centi down to pico? How many steps? 4. So you're going to take that decimal point and move it 4 places to the... No, we went down on the chart, right? From centi down, so we moved to the right. So 1, 2, 3, 4. So what do you get? 9,800? Do you all see it or not? No? Do you see centi on the chart? Okay. So centi, below centi is milli, then micro, then nano, then pico, right? So if we have 0.98 centigrams, and we want to know how many picograms that is, we're going to move 1, 2, 3, 4 places down our chart. 4 places, and when we go down, we always move the decimal point to the right. No? Let me give you another one. How about 31,472 nanometers? That's an N, nanometers. Turn that into kilometers. So find nano. The abbreviation, the symbol is N. Meters is our unit. So what does it take to go from nano up to kilo? How many? 8 steps. So we're going to go 8 steps. And where's the decimal here? After the 2. And which way do we move the decimal? To the left, because we went up on the chart. So 1, 2, 3, 4, 5, 6, 7, 8. That's going to create this number, 0.003142 kilometers. Are y'all okay with that? Moving around on this chart or no? Y'all look all confused. Do we need more? Okay, everyone's going to ignore me. Is it 3 zeros? Hold on. 1, 2, 3. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8. Okay, thank you. It's 3 zeros. I did a jump over the little comma. That's not counted. Thank you. That makes me feel good. If you all look confused, maybe that means I messed something up. Now may I proceed? Okay. All right, so now there's some other conversion factors that will help us get from metric system over to the US standard system. And there's some other conversions that we need to know. Like if you want to know how many liters are in a gallon, or if you want to convert miles to feet, things like that, it's all on here. So we're just going to try and do some conversions now. But it's going to be very different than this. This is nice. Metric, you just move decimal points around. That's all it is. Figure out how many jumps on the scale and move accordingly. But if we want to do something like converting 21.5 inches, IN meaning inches, is how many centimeters? Well, there is no nice little chart that you can just jump across and move decimals, because centimeters, the standard unit for this measurement of length is a meter, and over here we're using inches, which means feet and yards. So the question is, how do we get there? So I'm going to show you, this is very different than what we just did. What I'm going to do is I'm going to write down 21.5 inches over 1. And I'm going to start using, this is called dimensional analysis. We are going to try and kill off the units. We're going to try and kill inches off and create centimeters. That's what we want. So look on this right here and tell me if you find anything that relates inches and centimeters together. Okay, so on this sheet, and I'm just going to write it down here. I'm not going to do it over here. I know that 1 inch equals 2.54 centimeters. Do you all see that on your chart? How am I going to use that over here to kill off inches and create centimeters? Multiply this by a fraction, right? Inches down here, centimeters up here. And what we can do is we'll get our units to cancel. So you need to tell me how many centimeters are or what's the relationship between centimeters and inches? 2.54 centimeters in what? 1 inch. Do y'all follow what I did here? This is what I was interested in, so I wrote it as a fraction. I know I want to go from inches to centimeters, so I came up with what we call a conversion factor. This is it right here. I wrote it as a ratio, as a fraction, putting centimeters on top of inches so that my inches will kill off. Inches go away, and I'm left with what? What is that on your calculator? 54.64? 61 centimeters. That's what we're getting. We're going to be able to practice these a little more. How about this? 120 meters to yards. 120 meters equals how many yards? So the way I like to start this off, I write 120 meters over 1 times, and now I ask myself, is there something on here that connects meters and yards together? Is there? Do you see anything? Yeah, there's nothing that is a direct connection between a meter and a yard, right? The best you have is that 1 yard is 3 feet, right? 1 yard is 3 feet. So I'm just going to write that down. I know that 1 yard is equal to 3 feet. That does not work because we have meters and we have yards. I have yards here and feet here. So I know I can get from yards to feet with this, right? Is there any way you can get from feet to meters? Yes? Where is it? 1 foot is what? 0.348 meters, right? So these are the two conversion factors that would allow me to go, what, you could go from meters to feet, from feet to yards, or you could say it the other way around. To get to yards, I can come from feet, right? Feet, meters. Make sense? But I'm going to work with this as a fraction. So help me out. How are you going to do this? I need the meters to cancel, don't I? So you've got to put something with meters down here. And the only thing you have is what? This one? So I'm going to put 0.3048 meters. And up here, what's up here? 1 foot, right? That's this right here. So right now I know that my meters would cancel, wouldn't they? I'd be left with feet, but I don't want feet, I want yards. So I come in here with another conversion factor next to it. And what am I trying to kill off now? The feet, right? Because the meters are going to be gone. The feet down here, and I want yards up here, because that's what I want my final answer to be in. So what's my relationship between feet and yards? 1 yard is 3 feet. And these feet now cancel.
If you wanted to, instead of the 0.3048, do you put the 1 meter equals 3.280 feet, and then from feet?
Which one? Oh, use the other factor? Yes, you could have. Yep. Questions, though, on this? You sure?
Because every time I multiply decimals, it comes out as a fraction. I wasn't sure if you knew that.
Let me see. You should have a button on here.
If I multiply 0.3048 times 3, it gives me a fraction.
Just hit this button right here, SD.
Okay.
Okay, so if I go 3 divided by 4, it goes 3/4, hit SD, it's 0.75. All right, so I'm going to multiply just the numbers across. 120 times 1 times 1, so I get 120 yards over, and then these numbers, 1 times this times this. So I need to get my calculator and do that. And I get 0.9144. And notice that all the units are gone, so it's just a number down there. And now do 120 divided by that number. Anybody else getting 131.23-ish? Yes? So this is approximately 131.23 yards. And just so you know, this like wavy equal sign is an actual mathematical symbol we use to say approximately. What do y'all think? All right, the next one's kind of tricky. I think what I'll do is I'll start off with something a little easier. Let's go 2 inches squared equals how many centimeters squared? So I'm going to start with this because I think it'll be easier for us to understand what's going on. When you see a little squared on that little unit right there, that does not mean square the 2. All right, this doesn't mean 4. This squared tells you that you're no longer talking about the length of something, you're talking about what? What's the unit of measurement? Area of something. All right, so if you have just, for example, inches, right? This is a measurement of length. If you have inches squared, this is a measurement of area. If you have inches cubed, this is a measurement of volume. And then inches to the 4th doesn't really make sense in our physical world, all right? So if I say, you know, this table is so many inches long, that's a length. If I say inches squared, that means I measured, let's say I want to paint this wall, I measure the length times the height. That number would be, you would say it's, let's say, 400 square inches. And by saying inches squared or square inches, you're letting the person know it's a measurement of area as opposed to length. Cubic inches is a measurement of volume. So the question here is, If you have 2 square inches, how many cubic centimeters, I mean, square centimeters is that? So let me try and draw a picture here. If I have 1 inch and 2 inches here, would you agree that this area would be 2 square inches? It would be this. Yes? The question we're asking is how many square centimeters can I get inside of that? So if you take a centimeter, that's 1 square centimeter, maybe there's 2, there's 3, there's 4. So how many square centimeters are in 2 square inches? With me? That's physically, geometrically what's happening. But we're still going to go to this, but it's going to be different than what we had before. Do you have in here anything with square inches? Don't, do you? No square inches on here. But you have inches, don't you? Do you have anything that relates inches to centimeters? You do. I have this. 1 inch is equal to 2.54 centimeters. Yeah? The mistake that people will make is they'll just like square both sides of this or something. It's not correct. So let me do what we did before. I'm going to write down what we're given. 2 inches squared over 1. And what do I need to get to cancel? The inches squared, don't I? And to get the inches squared to cancel, that means I'm going to need 2 factors of inches down here. And I want what to appear? I want the inches squared to cancel, but I want what to appear? Centimeters squared. So there's 2 ways you could look at doing this. I could do inches, centimeters, inches, centimeters again. Wouldn't this, if I put this together, if I multiplied this, inches and inches would become inches squared and would cancel with inches squared? And centimeter would go together and become centimeter squared? Yeah? Do you have a relationship between inches and centimeters? Yes. So I go 2.54 over 1, 2.54 over 1. Do you see that? I have to do it twice because I have 2 units here, units squared. And now cancel out your units, inches, inches, inches squared, and multiply everything across the top. So 2 times 2.54 times 2.54. 12.90, something like that. 12.90, we'll just go with that. Centimeters squared over what? 1, so this is good. Let's see if you can use the same sort of idea to do the following problem. Could you convert (22) cubic meters into cubic feet? I want you to work on this one. See where we are. We got 5 minutes left. Let's see if you can do that. We're not going to quite get through conversions today. So I would say for your homework, just do through proportions. Right? I'll write that down here. Homework, just through proportions. And if you want to, you can do conversions section of homework, part A. So if you get this answer, I want you to raise your hand. I'll come by and see if you're there. If you're having trouble or you just want to know if you're setting it up right, raise your hand. I'll come and tell you.